Hello again. Today I'm going to talk about recent comparisons I've seen on forums about fuzzy logic and PID control. And I'm not going to compare fuzzy logic directly with exactly PID control because sometimes you need an integrator, sometimes you don't. So it's going to be some variation of PID control. Anyway, there's a document that I found on the internet that someone pointed to, and it's over here. I'm going to not show the top part to hide the name of the author because I'm going to totally trash him out. Anyway, you can see that this is about PID control, and he's using Ziegler-Nichols technique for tuning the PID. Now, Ziegler-Nichols is not a very good way of tuning a PID, and especially a higher order system like the example that the author uses here. So let's just get started. And first part's just doing some introductory work. And this is the first part of interest. You can see that he knows what the plant is. This is the open loop plant, and this is the same thing that I have over here. I call it an actuator, so I call it G sub A. But you can see we're using the same Laplace transform to represent the open loop plant. And you can see his closed loop plant is here. And now what he is doing is he's trying to apply the Ziegler-Nichols method of tuning to his plant. And this is a very good way of trying to make a PID look bad. And it's very easy to make a fuzzy logic controller look good if you make the PID look bad. And that's exactly what this author does. So this shouldn't have been accepted as a paper. And you can see that this was accepted by the Proceedings of World Congress on Engineering and Computer Science in 2007. And you would think that someone with some intelligence or knowledge of control would have reviewed it before it got published. Anyway, he shows a response. This is the response for his Ziegler-Nichols over here. And you can see that it isn't really very good. There's an awful lot of overshoot, which is what you'd expect with Ziegler-Nichols. And also, Ziegler-Nichols just wasn't meant to tune every type of system, especially integrating systems like this one is. You can see this is an integrating system because there's an extra S out here. So if this was representing velocity, this S would be integrating velocity into position. So this is an integrating system. Coming on down, he decides to make a little bit of a correction on the PID gains, but you can see he's got a P, I, and D here, and he gets the response just a little bit better, but it still has a lot of overshoot, and the settling time is very poor. So now let's get into the fuzzy logic controller. And what you can notice here is that he's using only the error and the derivative of the error. And this is kind of interesting because first thing is, how do you integrate an error on a fuzzy logic controller? You still would have to have some sort of integrator that's kind of like what the PID would need if you wanted to use a integrator on a fuzzy logic controller. Also, whenever you use an integrator on a PID on a step jump, there's a good chance it's going to overshoot because during this time here, the integrator winds up, so that it has to overshoot to unwind. So again, this is going to make the proportional or the PID controller look bad. And by not having an integrator, he doesn't have to worry about that. And he doesn't have to worry about the integrator also because the system is already an integrating system. You only need one integrator, but that's in theory. In a real motion control system, you would have an integrator to integrate velocity into position, and that would be the physical plant. And then also you would have a PID control for integrating to just make use of, to close the final gaps, because usually there's a little bit of friction at the very end. So anyway, coming down to here, you can see his response with the fuzzy logic controller. And if you read his conclusion, he's very proud of that. And actually, it's not very good. So let's compare his fuzzy logic with my control, and I'm going to use a method of calculating the gains. So I'm starting out with the same plant that the fuzzy logic author used, and I have a closed loop transfer function here. I simplify it. And then this is the closed loop transfer function. It's the same thing as what I have over here. I just left out the s's because I'm trying to solve this symbolically, and I can't do that if these are functions. So I'm solving for the controller. So the controller, this is the equation for the controller. And since I know I can specify the closed loop transfer function here, which is basically two real poles. And so what I'm going to do is have, then I calculate the controller function here. So this is the controller function. Now this is not a PID. You have to kind of look at this to be able to figure out what kind of system it really is. And as it turns out, it's a PD with a second derivative gain. Also, there's a low-pass filter. So what I did is I took this original equation here and I converted it to a PD2 controller with a low-pass filter with a pole at 2 times lambda. And lambda is a tuning parameter, just like in my other examples where I can increase lambda to get a faster response. So using this equation, this is the equation for the proportional gain, the derivative gain, and the second derivative gain, and these are the gains that I calculate. And if I want to, I can make this lambda bigger, and I would have even higher gains and a slightly faster response. So let's go on down. This is the calculations for the state space arrays for the open loop part of it. And I got to convert the continuous time domain into discrete time domain. I've done this on many of my other videos. Oops, skipped a little bit here. I have my PD2 controller, which is pretty basic. This is a basic state space update the current state with the current output. And you can see I'm starting at 0 for my position, velocity, and acceleration. That's my initial output. And then this is implementing the low-pass filter. So now I have a target generator where I'm just doing some steps. I'm doing a step jump to 1, -1, and negative 0.05. The author over here just did a step from 0 to 1. So I'm going to have a little bit more activity. So over here, you can see this is the response that I get as I go to 1, -1, and 1, and you can see the control output. So what is happening here is you can see my response is much faster than the response over here. Also, you can see going down and going up that my response is much faster. So let's just take a look at the Bode plot. You can see the Bode plot has, since my desired transfer function has 2 real poles, you can see it has at the higher frequencies a phase delay of 2 times 90 degrees, which is 180 degrees. And then I'm plotting my poles in zeros down here. And the closed loop transfer function has got 3 poles, and as it turns out, the method I use will cancel out 2 of them, so I get a response of just this 1 pole here at minus 20. So you can see that my PID, or my PD2 control, is much better than the fuzzy logic control. The point that I'm really trying to make is that I see a lot of articles, papers, where they're trying to make fuzzy logic look good relative to a PID control, and usually these people do not know how to tune a PID controller. So if they make the PID controller look bad, obviously the fuzzy logic controller will look good in comparison. But what I don't like about it is it misleads an awful lot of people, and also it demonstrates an ignorance of how to tune a PID. That's all.